Swayam Prabha. Digital India. Educated India.
I welcome you all to lecture number 30 on the topic flow through heat exchangers. This is the continuation of the topic which we have discussed in the previous lecture number 29. So, yesterday in the lecture number 29 we have seen the flow through heat exchanger, especially the method of analysis of heat exchangers by LMTD method. If we classify the heat exchangers, we can classify based on the type of the direction of flow. If both the hot and cold fluids flow in the same direction, then it is called parallel flow. If the flow of hot and cold fluid are in the opposite direction, then it is called counter flow. Then according to the construction, we can classify the heat exchangers as shell and tube, shell and coil, tube in tube, etc. Shell and tube fluid, hot fluid passes through this the shell portion, and in the tube portion the other fluid passes. It can be the other way also. In case of shell and coil heat exchanger, the tube portion which is in the shell and tube is replaced by a coil, otherwise the construction is almost same. In case of a tube in tube heat exchanger, there is a fluid flow first inside in the first tube the fluid flows, one fluid flows, and outside the first tube there is one more tube. In the annulus, that is the gap between the first inner tube and the outer tube, the other fluid flows for the heat transfer. So, when there is heat transfer between the hot fluid and the cold fluid, the hot fluid is being cooled from capital T1 to capital T2, and the cold fluid is being heated from small t1 to small t2. Small t1 and t2 refers to the inlet and outlet temperature of the cold fluid, and capital T1 and T2 refers to the inlet and outlet temperatures of the hot fluid. So, if we see the analysis of the heat exchanger, we have used two equations primarily, LMTD for parallel flow and LMTD for counter flow, logarithmic mean temperature difference. So, once we calculate the LMTD, we can, if the overall heat transfer coefficient which is U, which differs from the convective heat transfer coefficient H. Overall heat transfer coefficient, it takes into account the conduction resistance, resistance due to convection, etc. Generally, these radiation effects are neglected in these calculations. Of course, if we consider the fouling resistance which is there on the inner side, which is on the tube side, and which is as well as which is on the shell side of the heat exchanger, then the total resistance will increase and it will affect the rate of heat flow. And we have solved some numerical questions based on the LMTD method. If we see, if logarithmic mean temperature difference value is 0, for example, if we are when we are calculating either for a parallel flow or for a counter flow, if LMTD equal to 0, then we have to take that, then it indicates the temperature difference, that is capital T1 minus small t2, that is hot fluid inlet temperature minus cold fluid outlet temperature will be equal to the hot fluid outlet temperature capital T2 minus cold fluid inlet temperature. So, it is capital T1 minus small t2 or capital T2 minus small t1. So, that is the LMTD value which we have to take and proceed with the calculations. And we have seen the applications of few applications of the heat exchangers. Of course, if we list out the applications in which heat exchangers are used, the list is a very big list. So, I have given in a single slide the summary of the very few applications of the heat exchangers. Now, let us continue with the same topic, but in this lecture we are going to analyze the heat exchanger, design the heat exchanger by NTU method. So, it is a brief introduction why we are going for the NTU method, then how to do the analysis, heat exchanger analysis using NTU method, and few numerical questions. If we take, if we have a look at the LMTD method, if we want to find out the LMTD of heat exchanger irrespective of the direction of flow, whether it is parallel flow or counter flow, we should know all the 4 temperatures, that is inlet temperatures of both hot and cold fluid and outlet temperatures of both hot and cold fluid. Unless we know all the 4 temperatures, it is not possible to find the LMTD of a heat exchanger. So, this method, it is a very simpler method, very easy method, and if we know the temperatures, all the 4 temperatures, then we can find out the LMTD of parallel or counter flow. So, there is, suppose if 2 temperatures are given, in case if we have 3 temperatures are given, hot fluid inlet and outlet are given, cold fluid any one inlet, mostly inlet temperature will be given. So, that means we can find the rate of heat flow, that is how much heat is lost by the hot fluid, or if you know both the cold fluid, both the temperatures of the cold fluid, we can find how much heat is gained by the cold fluid, provided we know the mass flow rate. If the fluid used is either water or air, so even if Cp is not specifically given, we can take the standard values. Cp of water is 4.18 kilojoule per kg Kelvin and Cp of air is 1.005 kilojoule per kg Kelvin. So, but if mass flow rate is not given either for the hot fluid or cold fluid, then we will not be able to find out the value of Q. Once we know the value of Q, and if the other fluid mass flow rate as well as if one temperature is known, we can find out the 4th temperature, we can find out the unknown temperature. So, LMTD method cannot be employed if 2 temperatures are unknown. Okay. So, suppose if inlet temperature of the hot fluid and inlet temperature of the cold fluid is given, capital T1 and small t1, that means we will not be able to find out, because we cannot find out the value of Q also, MCP, using the basic relation MCP delta T. So, there is a limitation on employing this type of method, especially if we do not know the temperatures, all the temperatures. NTU method can be used to design the heat exchanger even if 2 temperatures. So, normally those 2 temperatures that will be given as capital T1, that is hot fluid inlet temperature, and small t1 cold fluid inlet temperature. So, in the case of LMTD method, we use the relation UA LMTD, where LMTD the formulas are different for parallel flow and counter flow. So, here NTU stands for number of transfer unit, that is equal to overall heat transfer coefficient into the heat transfer area, surface area for the heat transfer to take place, divided by C minimum. Let us see what is the C minimum, CH and all. So, here if you see U, there is no change, the overall heat transfer coefficient in watts per meter square Kelvin or degree centigrade. A is the heat transfer area in meter square. C minimum is the minimum of CH or CC. So, C minimum is the minimum of CH or CC. Capital C subscript small h and capital C subscript. So, here H refers hot fluid, C refers cold fluid. So, here CH means heat capacity. So, heat capacity is nothing but, let me write it here. Okay. Heat capacity is represented by the letter capital C. So, it is the product of mass flow rate into specific heat. The product of mass flow rate of the fluid and its specific heat is called as heat capacity. Since we are using 2 fluids, one is hot, another one is cold fluid. So, CH refers to heat capacity of the hot fluid. So, that means m dot will become m dot h and Cp will become Cph. Similarly, this is for hot fluid and C is mass flow rate into specific heat. For the cold fluid, C suffix small c into m dot c into Cp of this. So, the product of mass flow rate of that particular fluid and its specific heat will give you the heat capacity. So, if you see the units heat capacity, okay, if you see the mass flow rate is in kg per second, specific heat capacity is in kilojoule per kg Kelvin or degree centigrade. Okay. So, kg and kg will get cancelled, we will get kilojoules per second Kelvin. Kilojoules per second is nothing but kilowatts by Kelvin. So, this is the unit of heat capacity. So, heat capacity is the product of mass flow rate of the fluid and its specific heat. So, let us go to this one. So, that is what I have written here. So, it is m dot. Okay. So, due to the compatibility, I think it is not clear. So, specific heat of the, so heat capacity of the hot fluid is the product of m dot h into Cph. So, the unit is kilowatt per Kelvin or watts per Kelvin. So, the other Cc is for the cold fluid. This NTU method is also known as effectiveness method. And how to define the effectiveness of a heat exchanger? It is the ratio of actual heat transfer to the maximum possible heat transfer. For example, if you are cooling, let us take the inlet temperature of the hot fluid as 100 degrees centigrade. Okay. So, inlet temperature is 100 degrees centigrade, capital T1 is 100 degrees centigrade. This is hot fluid inlet, So, let me emphasize again, throughout the calculations in the NTU method also we will be using capital T1 and T2 for hot fluid, small t1 and T2 for cold fluid. Let us take the cold fluid inlet temperature is 30 degrees centigrade. So, if you compare capital T1 and small t1, the hot fluid is being cooled while the cold fluid is being heated. So, the maximum possible heat transfer, I can cool the hot fluid up to a temperature of, up to a inlet temperature of the cold fluid only. That means, in this example which I have taken, I can cool the hot fluid from 100 up to 30, not below 30. That means, similarly, cold fluid can be heated from 30 to a maximum temperature of 100. That means, hot fluid can be cooled up to the inlet temperature of the cold fluid can be heated up to the inlet temperature of the hot fluid. So, neither of this process can go above or below the value of capital T1 or small t1. So, this one is this capital T1, this difference is the maximum possible heat transfer. So, this is called maximum possible heat transfer. Once again, let me repeat, the hot fluid can be cooled up to a temperature of, up to a particular temperature, that temperature is equal to the inlet temperature of the cold fluid. In this case, I cannot cool 100 hot fluid below 30, that is cooling from 100 to 20 or 25, it is not possible, because the inlet temperature of the cold fluid is 30 in this example. Similarly, the cold fluid can be heated up to a temperature of 100 degree centigrade, which is the inlet temperature of the hot fluid. We cannot heat it above 100, above 100. So, this difference is the maximum possible heat transfer. Of course, mass flow rate and all will come. I have just mentioned, explained only based on the temperature difference multiplied by mass flow rate will be. Otherwise, this is not come. Q max is, this is MCP will be there. MCP value will be there. Okay. So, that is say. So, of course, the numerator. So, it is the ratio of actual heat transfer. Actual heat transfer may not be T1 to small t1. It can be T1 to capital T2, from T1 to T2. In actual process, the hot fluid might be cooled from 100 to 50. That means, the numerator is 100 minus 50 divided by the denominator is 100 minus 30. So, that is 50 by 70. Okay. So, the effectiveness will, accordingly will be around 70 or 75%. Similarly, if you take the cold fluid, small t2, the outlet temperature of the cold fluid minus inlet temperature of the cold fluid. So, that is the actual heat transfer, So, I can heat the cold fluid from 30 to 75. That means, the delta T is 75 minus 30, which is 45. Denominator will remain the same. Denominator maximum possible heat transfer is always this one. Okay. It's always this one. Let me write into MCP. Okay. So, the ratio of actual heat transfer to the maximum possible extent that heat transfer can take place, that is called effectiveness of the heat exchanger. So, the NTU method is also called as effectiveness method. So, here, I have just in terms of formula Q actual by Q max. So, if we see the previous one, C minimum, minimum of heat capacity of hot fluid or heat capacity of cold fluid, whichever value is small, that is the minimum heat capacity value. This is the minimum heat capacity value. Capital C refers to heat capacity. So, suppose if the minimum heat capacity is corresponding to the hot fluid, that is C minimum equal to CH, then the effectiveness formula is, in the numerator I will have only hot fluid temperature. If C minimum is equal to CH, if C minimum equal to CH, then I will have only hot fluid temperatures T1 and T2. Capital T is hot fluid, small t is cold fluid. Denominator will be the same. So, this is the actual heat transfer. The hot fluid is being cooled from a temperature of T1 to a temperature of T2. So, in this example it could be 100, from 100 to maybe more than 30, it cannot be less than 30 or equal to 30. If capital T2 and capital T2 is equal to small t1, then the effectiveness of the heat exchanger will become 100, numerator and denominator will be 1, the ratio will be 1. If the heat capacity, minimum heat capacity is corresponding to the cold fluid, then the numerator will contain only the temperatures of the cold fluid. Temperature of the cold fluid are small t1 and small t2. Small t1 is the inlet temperature of the cold fluid and small t2 is the outlet temperature of the cold fluid. So, higher temperature minus lower temperature. So, small t2 minus t1. This is the actual heat transfer. So, the example which I have taken, the cold fluid is being heated from 30. Maximum it can be heated up to 100, but if in the actual heat transfer it may be 90 degree. So, 90 minus 30, that is 60 divided by 100 minus 30. So, it will be around 85 or 90%, the effectiveness will be. Again here also, if small t2 is small, if the temperature to which it is heated, if small t2 becomes t1, if small t2 becomes capital T1, then the numerator and denominator will become 1. So, the effectiveness will be 100%. So, in this case, if T2, okay, so let me write, if capital T2 is equal to small t1, then effectiveness is equal to 1, that is 100% or 100%. Similarly, if T2 is equal to T1. Similarly, if small t2 is equal to capital T1, then also the effectiveness is equal to 1 or 100%. So, what does this indicate? Outlet temperature of the hot fluid is equal to the inlet temperature of the cold fluid, which is the maximum cooling that can be attained in this case. 100 degree hot fluid can be cooled to a maximum of 30 degree cold fluid inlet temperature. Similarly, so this is if T2 equal to T1, let me write it clearly, T2 equal to T1. Similarly, if the outlet temperature of the cold fluid is equal to the inlet temperature of hot fluid, then the ratio will become 1, which indicates that the effectiveness is 100%. So, the formula of in LMTD method we use Q equal to U into A into LMTD. So, here effectiveness of the heat exchanger into C minimum. If C minimum is hot fluid, I will write m dot mass flow to the hot fluid into specific heat, into its specific heat. If C minimum is cold fluid, then here instead of C minimum you have to write the mass flow of the cold fluid multiplied by its specific heat. Okay. So, this is capital T1 minus small t1, this remains the same, this remains the same, only the difference lies here only. Okay. Otherwise, epsilon, that is a symbol used to represent the effectiveness of the heat exchanger, that will remain the same, T1 and T2, only this will change according to the heat capacity. So, with this background, let us solve some numerical question. Okay, water at 80 degrees centigrade enters a counter flow heat exchanger. So, it is given as a counter flow with a mass flow rate of 0.5 kg per second. Okay, so, let me write here if any m dot is there. Okay, I think I have written this is m dot. Okay, there is no correction required. So, with a mass flow rate of 0.5 degrees centigrade. Here you see the inlet temperature of the water is 80. Whatever the temperature, suppose if it is given water is entering at 80, air is entering the heat exchanger 30, that means it refers to the inlet temperature. It does not represent the outlet temperature of the fluid. Air enters at 30 with a mass flow rate of 2.09 kg per second. If the effectiveness of the heat exchanger is 80%, determine the LMTD. So, here if you see only two temperatures are given. One is capital T1 and another one is small t1. That is, both the hot fluid and cold fluid inlet temperatures are given. Outlet temperature of the hot fluid is not given. Similarly, the outlet temperature of the cold fluid is also not given. So, there are only two temperatures. So, suppose if I have to use the LMTD method to find out the LMTD, so this is not, it is not possible. It is not possible because out of 4 temperatures only 2 temperatures are known. So, even if at least 3 temperatures are known, as I explained before, if the mass flow rate and the Cp of that fluid is known, then we can find out Q, either heat lost or heat gained. With that we can find the 4th temperature, but here it is only 2 temperatures are given. So, it is not possible to find out the other 2 temperatures using LMTD, because to determine LMTD we need all the 4 temperatures. Okay. So, let us take hot fluid and let us write the data given for cold fluid separately and the common data. So, if you take water at 80, this temperature is more, this temperature is less. So, obviously, the fluid which is entering at higher temperature than the other fluid, that should be the hot fluid. So, inlet temperature is given, hot fluid is water. So, we can write the fluid also, cold fluid is air. Okay. So, T1 is equal to 80 degrees centigrade, the corresponding inlet temperature of the cold fluid is 30. Because we know the fluids, so we can write the specific heat is 4.18 kilojoule per kg Kelvin, and here the specific heat is, so this is for cold fluid. So, I am using H for hot fluid and C for cold fluid, 1.005 kilojoule per kg Kelvin. So, there is one. So, the effectiveness of the heat exchanger is given as 80%, that is 0.8. So, that also we will write. So, epsilon is equal to 0.80. This is given in the problem. So, we have to find out first, unless we find out the LMTD, okay, we know the formula for LMTD of a counterflow heat exchanger, unless we find the, so before that let me write the formula. So, LMTD for counterflow, because the type of heat exchanger is clearly given in the question, counterflow heat exchanger. For counterflow heat exchanger, LMTD is equal to capital T1 minus small t2 minus capital T2 minus small t1 divided by ln of the first term divided by second term. So, the numerator is easy to remember. Of course, these formulas are given in the data book. In the subsequent slide, I have taken the scanned page of the HMT data book. So, I will show in which page number these formulas are available. So, this will be ln of T1 minus T2 divided by T2 minus T1. So, this ln is a common one, this ln is a common one. So, now if you see T1 is given and similarly small t1 is given, capital T1 and only small t1, but the other 2 temperatures are unknown, T2 and we do not know the temperature T2, outlet temperature of the hot fluid is not known. Similarly, outlet temperature of the cold fluid is also not known. So, unless these 2 find, and we have been asked to find out the LMTD. So, definitely the other 2 temperatures are required. Okay. So, now let us find out the heat capacity first, and before that one more data is given, mass flow rate is given. Cold fluid is, the air flow mass flow rate is 2.09, air is the cold fluid. So, let me write 2.09. So, m dot h is equal to 2.09 kg per second and hot fluid is 0.5 kg per second, that is water flow rate is also given. So, this is m dot h is equal to 0.5 kg per second. So, the mass flow rate is also given. Okay. So, let me write this one m dot h. Okay. So, this is m dot, this is m dot. So, the first step in the heat exchanger designed by NTU method, we have to find out the heat capacity. Okay. So, the heat capacity, let me again write heat capacity is equal heat capacity of hot fluid, that is CH, mass flow rate of that hot fluid multiplied by its Cp value, m dot h into Cph. So, m dot h is given, okay, 0.5. So, let me write it here, 0.5 into 4.18. So, we can find out the specific heat capacity of the hot fluid. Okay. So, it will be 2.10. 2.10. So, this is, as I explained the unit, this will be in kilowatt. If I am substituting the Cp value in kilojoules per kg Kelvin, so the resultant will be in kilowatts, kilowatts per Kelvin. Similarly, I am finding the heat capacity of the cold fluid, heat capacity of cold fluid. So, mass flow of the cold fluid into specific heat of the cold fluid. So, this is equal to 2.09 into 1.005. So, it comes to 2.1. So, here you find 2.10 kilowatts per Kelvin. Units are very important. Now, you compare the heat capacity of the hot and cold fluid, both are same. Since CH is equal to CC, therefore, the minimum heat capacity is both the heat capacity of the hot fluid as well as the heat capacity of the cold fluid. Therefore, C minimum is equal to CH, which is equal to CC. This is only applicable for this problem, okay, for any other numerical question in which both the fluid heat capacities are same. Okay. Now, I can use the effectiveness formula for if C minimum equal to CH. So, here if you see, I have given this, if C minimum equal to CH, then effectiveness of the heat exchanger is given. So, we can find out here in the effectiveness formula only 3 temperatures are involved. In the first effectiveness formula, capital T1, capital T2 and small t1. So, because we know capital T1 and small t1, we can find capital T2. Similarly, in the second effectiveness formula, which is pertaining to the cold fluid C minimum heat capacity. So, small t1, t2 and capital T1 are given. So, it is very easy to find out the other temperature since we know the effectiveness of the heat exchanger also. So, now, okay. So, use this formula C minimum equal to, let us take the first one, C minimum equal to CH. For this, the effectiveness formula is T1 minus T2 divided by T1 minus small t1. Here T1 is given, small t1 is also given. The only unknown is capital T2 and effectiveness is 80%. If you substitute the value, you will get T2, you will get T2. The capital T2 value is 40 degrees centigrade. So, the actual heat transfer for this case is the hot fluid is cooled from 80 to 40, but it can be cooled to a lowest temperature of 30 in this example. Okay. So, this is T2. Similarly, C minimum is equal to Cc because the heat capacity is same for both the fluids here. So, that means using this formula we can write the effectiveness formula T2 minus T1 divided by capital T1 minus small t1. Here also small t1, capital T1 is known, we can find the outlet temperature of the cold fluid, outlet temperature of the cold fluid. So, that comes to 70, that comes to 70. So, the cold fluid is heated from 30 to a maximum temperature, it can be heated up to the inlet temperature of the hot fluid which is 80, but here it is heated up to 70 only, up to 70. So, the actual heat transfer is 70 minus 30, 70 minus 30. Now I know these two temperatures. So all the temperatures are known, T2, small t2, all the temperatures are known. Substitute all the values, therefore substitute capital T1, capital T2, small t1, small t2 in LMTD for counter flow. You will get the answer as 10 degree. So here you get LMTD as 0, LMTD equal to 0. If you substitute in this formula, you will get LMTD equal to 0. Okay. If since LMTD equal to 0, therefore, let me write this. Since LMTD is equal to 0, therefore we have to take LMTD as LMTD is equal to capital T1 minus small t2. This will be equal to capital T2 minus small t1, which is equal to 10 degree. Okay. So that completes the problem. So this is the final answer. LMTD for the given question is 10 degree centigrade. So that's what I have calculated here. LMTD. So let me again repeat. If LMTD equal to 0, that means capital T1 minus small t2, that difference will be equal to capital T2 minus small t1. That is, the difference between the hot fluid inlet and cold fluid outlet will be equal to the difference between the hot fluid outlet and cold fluid inlet temperature. So that completes the problem. Now before moving to the second numerical question, in page number 160 of the data book, we will find the equations for LMTD method. This is the basic equation, Q equal to UA delta T LM or LMTD, both are same. Okay. This is page number, again let me emphasize, HMT data book by C.P. Godandraman, Subramaniam. There are two authors, by, so this is 9th edition. So there are new editions that have come after this. There will be, as I mentioned before, there will be slight changes in the page numbers. Maybe instead of 160, it may be 161 or 162. Suppose generally when a new version is released, there may be few updations, but there will not be any change in the page numbers significantly. So you can see, you can refer the index page and take the appropriate page number. So here you see, this is the parallel flow. This is the formula. For counter flow, this is the formula. So I have used the same representation, capital T hot fluid, small t cold fluid, and these are all the explanations given. What is capital T? See here, this is capital T, this is capital T2, this is small t1, this is small t2. F is the correction factor. If you are using correction factor, then the equation is this one. This is for correction factor, with correction factor. And in the same page, the NTU formula is also given. This is the formula for NTU. So here C minimum by C max is 0 if one of the fluid is either condensing or evaporating. Here I have given two formula, epsilon equal to MHCH by C minimum. If C minimum is CH, these terms will get cancelled. So that is why I am writing directly capital T1 minus capital T2 by capital T1 minus small t1. So actually this term will get cancelled. This term will get cancelled. Let me write it again. Epsilon is equal to MH CPH divided by C minimum into capital T1 minus capital T2 divided by small t2 minus small t1. This is the formula if C minimum equal to CH. What is capital CH? This is nothing but M dot H into CPH. So these two terms will get cancelled. So we will get capital T1 minus capital T2. So similarly in the other effectiveness formula, epsilon is equal to M dot C CPC divided by C minimum into T2 minus T1
T2 minus T1, denominator is same, T1 minus small t1, if C minimum is equal to Cc. So, these two terms will get cancelled. So, we can directly write, So, that is what is given here, Okay. So, let us move to the second question. A counterflow double pipe heat exchanger, is to heat water from 20 to 80. Okay. So, here also let me put to m dot. Okay. So, from what is the inlet temperature is 20, so it is heated up to 80, that means it should be a cold fluid, it is being heated. Okay. So, let me write this one, hot fluid cold fluid. The cold fluid used is water. So, initial temperature of the water is given, small t initial, both the temperatures are given, that is 20 to 80, 20 degrees centigrade, small T2 is equal to 80 degrees centigrade. This water is heated by the flow rate is given, flow rate of the water is given. So, let us write m dot C equal to 1.2 kg per second, m dot C is equal to 1.2 kg per second. So, this water is heated by, the heating is accomplished by geothermal water available at 160 degrees centigrade. Okay. So, that means that is also water, it should be a hot water. Okay. So, it should be a hot water. So, the hot fluid is also water. Okay. So, its temperature is given, inlet temperature is given 160 degrees centigrade. The inlet temperature of the hot fluid is given 160 degree centigrade and its flow rate is 2 kg per second. So, the mass flow rate of the hot fluid is given, So, it is 2 kg per second. So, here T2 is not given, capital T2 is not given, but 3 temperatures are given. Since 3 temperatures are given, both the mass flow rate are given, both the fluids are water, we know the Cp value, Cp value we can write it, whether it is hot water or cold water, 4.18 kilojoule per kg Kelvin, and similarly Cp of cold water is 4.18 kilojoule per kg Kelvin. Okay. So, as usual we have to find out the heat capacity. Okay. So, the first step in NTU method is always to find out the heat capacity. If you want to solve the problem by NTU method, then both the flow rates of the fluid should be known, otherwise we cannot find out the heat capacity. So, heat capacity CH is equal to m dot H into specific heat of the hot fluid. Similarly, here cold fluid is equal to m dot C. So, let me write heat capacity. So, this is heat capacity. So, m dot H. So, these values are known, So, we can substitute and find out CH. The CH value is 8.36 kilowatt per Kelvin. And these values are also known. So, Cc is equal to, the calculated value is, I have given a detailed calculation for all the numerical questions, but simultaneously I am doing it so that it will be easy for the students to understand. So, that will be 5 this is also will be mass flow rate. Okay. So, this also will be mass flow rate. So, dot will be there. So, that is 5.01. So, the heat capacity of the cold fluid is 5.01 kilowatts per Kelvin. So, heat capacity of the cold fluid is less than heat capacity of the hot fluid. Therefore, C minimum is equal to, the minimum of these two heat capacities, this is minimum, C minimum equal to Cc. For the previous problem, both the heat capacities were same. So, we wrote C minimum equal to CH and C minimum equal to CC, but here we should not write C minimum equal to CH. CH is C maximum, CH is C maximum. There are two fluids, so both of them are having the respective heat capacity. So if one value is minimum, the other value should be maximum out of the two. Okay. So here C minimum equal to CC, that therefore C maximum is equal to CH, C maximum is CH, okay, C maximum is CH, but C minimum is CC. Okay. So that is what. Now there is one ratio, okay, I am going to solve this problem by using chart. This is the effectiveness for counterflow, effectiveness of counterflow. This ratio is called C minimum by C maximum. This is called C minimum by C maximum. This ratio, the ratio of minimum heat capacity to maximum heat capacity, that is represented by the letter capital C, which you will find it, okay. So that is capital C, and the x axis is, this is NTU, this is NTU, the x axis is NTU, y axis is effectiveness. So I know C minimum, the C maximum is the other fluid. C minimum in this example, in this numerical question is heat capacity of the cold fluid. That means heat capacity of the hot fluid should be the maximum. So I know this ratio. So I have to find out this ratio. Okay. So I am finding the ratio C. So next step is capital C is equal to C minimum divided by C maximum. What is C minimum? C minimum is CC, C maximum is CH. So substitute the value 5.01 divided by 8.36. Therefore, capital C is equal to capital C equal to 0.60, 0.60. Now this way, so I know where is this 0.60, 0.60, this is 0, 0.2, 0.4, 0.6. So this line, so this curve is capital C is equal to 0.60. This is our calculated value. This is our calculated value. Now if I know any one, either y axis effectiveness, if I know, I can find NTU, or if I know NTU, I can find effectiveness, because I know this, the inclined curve value, that is capital C, which is nothing but C minimum by C maximum. Now we have been asked to find out the L. If you want to find out the length of the heat exchanger, we should know the surface area. So pi dl, okay, pi dl. So if we want to know the surface area, I have to find out, I have to use the formula NTU equal to U into A by C minimum. Let me check with the numerical question. U is given, so yes, the overall heat transfer coefficient is given. So the data we have to write it here. So the U value is also given. U value is given as 640 watt per meter square degree centigrade. This is given in the question. So U into A by C minimum. C minimum we know. Okay. U is given in the problem. So if we find out the NTU equal to U into A by C minimum. So U is given in the problem. C minimum we have calculated. If we find the NTU from this chart, then I can find out the area. Once I know the area is, that is nothing but pi dl, I can find out the length of the heat exchanger. The diameter is also given. Okay, so the diameter is also given. This is the diameter, 1.5 centimeter. So let us write that also. So diameter is also given 1.5 centimeter, that is equal to 0.015 meter. So now our next step is to find out the effectiveness, epsilon. Once I know the epsilon, okay, once I know the effectiveness value, the C value is known. So using these two, I will find out the NTU. Once I know the NTU, I can find area. Okay. Now here we have to use this one. Okay, effectiveness is yes. To find out the effectiveness, we can use this formula, Q actual by Q max, Q actual by Q max. Effectiveness is equal to Q actual divided by Q max. Okay. Q actual is this value MCP. Okay. Q actual is equal to mass flow of the cold fluid into Cp of the cold fluid into T2 minus T1. All the values you know, we know all these values. Okay, all these values are given. You see here, Q actual T1 we know, T2 we know, mass flow rate we know, Cp of water we know. So, we can find the Q actual. So, the Q actual value is this much 301 kilowatt. Okay, 301 kilowatt. Now, I have found Q actual. What is Q max? Q max is, okay, so this formula C minimum into T1 minus T1. C minimum into capital T1 minus small t1. Always maximum heat transfer is the temperature is inlet temperature of the hot fluid and minus inlet temperature of the cold fluid. What is C minimum? C minimum is Cc. For this problem, C minimum is Cc into T1 minus T1. Okay. So, let me write it here, let me write it below it so that it will be easy. So, this is nothing but Cc into T1 minus small t1. So, this is equal to Cc is nothing but we have found that is mass flow rate of the cold fluid multiplied by its capacity. So, the Q max is the maximum possible heat transfer is 701. So, this is Q max, this is Q max. Okay. The other one is Q actual. So, here also m dot will come, here also m dot. So, 701.4, 701.4 kilowatt. Now, I know this value also. So, substitute therefore, epsilon is equal to Q actual by Q max, which is equal to Q actual is 301 kilowatt divided by 701.4. So, we will get the ratio as 43% or 0.43, 0.43. So, epsilon is equal to 0.43. Now, I am going to use the chart 0.43. Okay. So, this is 40%, this is 50%, 0.43 will come here, this is 0.43, 0.43 is nothing but 43 percentage. Okay. So, this is nothing but 43 percentage. So, if you use the chart, this is 43 percentage. Okay, this is 43 percentage. So, I know the epsilon value, I know the C value. So, find out the intersection point. So, the next one is from heat and mass transfer data book, page number 172. Okay, so, this is page number 172, page number 172. C value is 0.60, which we have calculated, and epsilon value is 0.43. Okay, so, the C value is 0.60 and epsilon equal to 0.43, which we have calculated just now. If we find out the NTU, okay. So, this line and here this is the 1, 2, 3 from the third, fourth curve. Okay. So, you will get somewhere else this point, somewhere else this point. Okay. So, this will be the intersection point. Okay. So, this is, and vertically if you find this one, so you will get, so here it is 0.65 and the x axis is NTU. Therefore, okay, from HMT data book, from HMT data book, page number 172, at C equal to 0.60 and the epsilon is equal to 43 percentage. Okay. Okay. NTU is equal to 0.65. Now, NTU is equal to, but NTU is equal to UA by C minimum. Therefore, U into A by C minimum is equal to 0.65. Here we know the value of C minimum, we know the value of U, therefore, the surface area can be found out. A is equal to 5.09 meter square. meter square. So, here let me emphasize one thing. NTU is from the chart, C minimum we know, U is given in watts. So, if C minimum is in watts, if C minimum is in kilowatts, U should be substituted in kilowatts. If C minimum is in watts, then U also should be in watts, otherwise there will be wrong answer. So, 5.09. Okay. So, here the U, if U is given in watts, so we have to change the C minimum into watts, do not substitute in kilowatts. If the numerator is substituted in kilowatts, then the denominator also to be substituted in kilowatts. So, A equal to, but A equal to pi dl, A is equal to pi dl equal to 5. So, this is a cylindrical component. Okay. So, this is equal to 5.09. Diameter is given. So, pi into diameter is 0.015 into L equal to 5.09. Therefore, length of the heat exchanger is 108 meter, 108.1 meter. So, that completes the. So, we have been asked to find out, determine the length of the heat exchanger required, determine the length of the heat exchanger. If you want to find out the length of the heat exchanger, we should know the surface area, because the diameter will be given. Okay. So, or if length is given, area is found out, we can find out the diameter, Okay. So, this chart is used if any two parameters are known. Mostly C will be known, because C minimum and C max we can find out. Either effectiveness will be given or NTU will be given. If effectiveness is given, we can find out NTU, or we can calculate. In this case, we can calculate effectiveness. So, let us move to the last numerical question. A double pipe parallel flow heat exchanger is used to cool 0.1 kg per second of oil. Specific heat is given at 120. So, this should be the hot fluid. Okay, let me quickly do this one, because the procedure is same. Hot fluid is oil, okay, and cold fluid. Let us write what is the cold fluid. By using cooling water. So, hot fluid is oil, cold fluid is cooling water. By using cooling water. So, the cold fluid is cooling water. Cooling water. So, what are the mass flow rate is m dot c, okay, this is m dot h. So, the hot fluid inlet temperature is 120, its mass flow rate is 0.1. So, mh is given, capital T1 is given, capital T1 is equal to 120 degree centigrade, its mass flow rate is given, okay, I think it is 0.1 kg per second. If you take the cold fluid, its inlet temperature is given T1 20 degree centigrade. The oil is cooled by using water, which enters the heat exchanger at 20, and its mass flow rate is given 0.25. So, this is 20 degree and its mass flow rate is 0.25 kg per second. Since it is water, we know its specific heat 4.18 kilojoule per kg Kelvin, and because this is oil, okay, so its specific heat is given, specific heat of the oil, this is specific heat of the oil, it is given 2.5. So, Cp of oil is given 2.5 kilojoule per kg Kelvin. Okay. So, only two temperatures are given. So, if you see the given data, there are only two temperatures, capital T1 and small t1, capital T2 is not given, capital T2 is not given. Similarly, small t2 is not given. So, we cannot solve this problem by LMTD method, we have to use only by we have to use only NTU method to solve this one. So, let me quickly this one. So, the usual procedure is find out CH, Cc, find out CH, then CC. Okay, so in this one for CH is equal to MH CPH, CC equal to M dot C CPC. Let me due to time constraint I have given the detailed procedure. So, let me calculate 0.25 and 1.045. 0.25 kilowatt per Kelvin, 1.045 kilowatt per Kelvin. So, if you compare CH and C minimum, CH is less than CC, therefore, C minimum is equal to CH. If C minimum is CH, C maximum will be equal to CC. So, we can find out the ratio, therefore, capital C is equal to C minimum by C max. Okay, so, this ratio comes to 0.24. See here, since CH is less than CC, therefore, C minimum is equal to this one. So, the ratio comes to 0.24. Okay. 0.25 divided by 1.045. So, the ratio comes to 0.24. So, C equal to 0.24. Here instead of using chart, we can use chart also. So, this chart can be used. This is for effectiveness parallel flow and this is the value of C and this is NTU. Only thing is this chart is to be used for parallel flow. The given type of heat exchanger is parallel flow. Okay. Now, U is given, A is given. Okay, see one more thing, if you see the problem, U value is given, heat transfer area is also given. So, 0.45 meter square, U is equal to 1000 watt per meter square Kelvin. Because U we know, A we know C minimum, then we can find NTU. Therefore, NTU is equal to, directly we can find UA by C minimum. U is 1000, area is 0.45 meter square. Again this is in watts, it is given in watts. So, the denominator should be substituted in watts only. Okay, 0.25 0.25 into 10 power 3. So, you will get NTU as 1.8, NTU as 1.8. So, that is what I have calculated, NTU is 1.8. So, here I am going to use the relation from heat and mass transfer data, but we can use the chart also, page number 161. Page number 161, double pipe parallel flow. I am going to use this equation, okay. Use this equation and find out the, for double pipe, use this equation and you will get the effectiveness 0.72. So, we have been asked to find out the effectiveness of heat exchanger and outlet temperature of the oil. Outlet temperature of the oil is capital T2, we can find out using this formula. So, now let me summarize. So, in this lecture we have seen the design and analysis of heat exchanger by NTU method. So, here this method can be used if we know two temperatures which cannot be solved by LMTD method. So, with this lecture we have completed the last topic in module 5 as well as the entire contents in the subject thermodynamics and thermal engineering. Thank you.